So yesterday we were talking about the importance of the second derivative, which told us whether a function was concave up or concave down if it had a positive second derivative at a value of x and it was concave up, and if it had a negative second derivative at a value of x, it was concave down. And we said we could use that to determine whether it was a maximum. Maximums are concave down and minimums are concave up. And I was thinking about the problem we worked yesterday. We found out that there was this point, x equals a half, where the second derivative was 0. And that was a possible point, what we called a possible point of inflection. A point of inflection is where it changes from concave up to concave down, which it was. And I thought, oh, well, why don't we go back and figure out if we can use the second derivative test to look at minimums and maximums. So I used the first derivative expression, which is f prime is equal to 3x squared minus 2x plus 9. That wasn't going to be easily factorable, so I said I'll just use the quadratic equation to figure out the values for x, where the first derivative goes to 0. And it turns out that if you look at the expression for the quadratic equation, if you look at the term in the parentheses, you get negative 2 squared, negative 2 is b, minus 4 times a times c, and that'll end up with a negative square root. So because you get a negative square root of a negative number, then there are no values of x where you have the first derivative equal to 0. So let's see what that function looks like. So we're going to plot the original function. And what we'll find out, there are no minimums or local minimums or maximums if I did everything correctly. So let's see, was x cubed minus x squared, x cubed minus x squared plus 9x plus 9. Okay, we'll plot that, and we'll zoom out a little bit in this direction. And you can see that's what it looks like. So that's exactly what I expected. So there's a point of inflection at 1/3. So the function changes from concave down. So the curve inside of the curve is pointing downward to concave up. And at x equals 1/3, you're switching from a negative second derivative to a positive second derivative. At that point, the second derivative is 0. But you can see we don't have those characteristic humps that we have seen in the past. And notice there's also just one x-intercept. That would that's not necessarily requires you to not have, you can still have minimums, local minimums and maximums without 2 intercepts, or 3 intercepts. But if you don't have local minimums and maximums, you're going to only have 1 intercept. So if you were using this, in this case, it would be, you could use pre-calculus to figure out what the x-intercept is, 1 x-intercept, and there's 1 y-intercept, and there's a point of inflection. So that would give you 3 points. It wouldn't help you. You'd probably have to pick other points somewhere outside of this area to give you enough information to do a reasonable sketch. So just to show you that the first derivative isn't always equal to 0, and that's what the curve looks like when that's happening. Okay, so moving on here. So we can't use that one. Let's pick a. Yeah, here's apparently one that does have those. So I'm going to work this one. Well, I'm trying to decide whether to let you guys do it. We'll work one more, and then I'll give you one to work on yourself. So, and we're going to actually do more than they ask for us. It says determine the intervals where f of x is concave up or down. Also, let's figure out where we have local minimums and maximums. Not using the first derivative test, but using the second derivative test. So find local minimum and maximum. Okay, So what we're going to do first is we're going to take the first derivative. So we get 3x squared minus 4x minus 5. Again, that doesn't look like something I could factor that easily, so I'm going to go ahead and find the critical numbers associated with that by setting this equal to 0 and then using the quadratic formula to figure out the values of x where this goes to 0. So you'd have x equals minus a negative 4 plus or minus the square root of negative 4 squared minus 4 times 3 times negative 5, all divided by 2 times 3. So that's minus b plus or minus the square root of b squared minus 4ac over 2a. So get my calculator out. So we'll get 4 plus or minus the square root of 76 divided by 6. And if we do decimals, 4 minus the square root 76 divided by 6. So we have one critical number, negative 0.79, and the second one at 2.12. Okay, so those are our critical numbers. Now the question is, are they local minimums and local maximums? We could use the first derivative test. We could make up a table, but we're going to use the second derivative test to do that. So to do that, to do the second derivative test, we need to take the second derivative. So f double prime of x is going to be 6x minus 4. So 2 times 3 is 6, and you just get rid of that, and you set that equal to 0. So you'll set that equal to 0. And you get x equals 4/6 or 2/3. Okay. So what we can do now with that, knowing that the second derivative is 0, this x value will set up our table for the second derivative. So we have interval x, f double prime x, some comment about concavity. So the interval here will be from negative infinity to, actually, yeah, that's right, negative infinity to 2/3, and from 2/3 to positive infinity. So pick x equals 0, x equals 1, and we'll evaluate the second derivative at those values of x. So f double prime of 0 is going to be negative 4, and f double prime of 1 is going to be 2. So you see, if I put 0 in here, I just have negative 4 left. If I put 1 in here, I'll get 6 minus 4, which is 2. So the second derivative is negative here and positive there, and so it's concave down, and this is concave up. If you think about that, concave down is kind of like that, and concave up is like that. So the second derivative test says that any value of x in this interval is going to be concave down. So if we go back to here, the value of x, negative 0.79, is in that first interval. And since negative 0.79 is the first interval, it's concave down, and therefore it's a local maximum. And the second number, 2.12, is in the second interval, and that's concave up, so we know that's going to be a local minimum. So I'm going to write that out in words so you can see the explanation of how you use the second derivative test. So we'll say since the critical number x equals negative 0.79 is in the interval from negative infinity to 2/3, the function is concave down at x equals negative 0.79, and therefore a local maximum. Also, since the critical number at x equals 2.12 is in the interval 2/3 to positive infinity, the function is concave up at x equals 2.12, and therefore a local minimum. Okay. So that's pretty much it for this section. So we're just gonna look at a couple of examples. Before we do that, though, I just wanted to talk about, this kind of relates to physics. You maybe don't want to hear about physics after yesterday. By the way, I mentioned to some people, and I mentioned it before the test, it's not unusual to people to not do super great on the second test. Not that it's an unreasonable test as far as time is concerned or difficulty, but part of the governor's school is learning about college classes, and so when you go to college, you have a kind of a feel for the level of difficulty. It's going to be harder than governor's school, and the tests a lot of times are more material. I try to give you as much time as possible to make the experience not as stressful, but I do like to put a little stress in there every once in a while. So there'll be some way that we'll work around getting you so that if you didn't finish the test or you didn't do very well on the test, to get you some extra credit. What I've done in the past is the problems that you do poorly on, I'll give you a problem similar to that you work on. So I'm not going to just let everybody work on well, it may be the same problem. Everybody may have the same problem they work on to make up for it. So I'm not just going to curve it a heck of a lot. I may curve it some, but I'm not going to curve it so that I get the average up just to some reasonable value. You'll have to do some extra work to redeem yourself to show that you finally do understand it. But typically everybody gets that credit, and they boost up their grade to a reasonable value, typical of what you would normally expect in that class based on the way you perform relative to your classmates. So don't get too stressed out about it. But anyway, so this is a sine wave, and if you take a spring and you attach a mass to the spring and you let it oscillate in the vertical direction, you've seen me do that in physics class. If you plotted position versus time, you would get a curve that looks something like this. And if the spring did not have any losses, it would just oscillate forever Of course, it doesn't do that. It actually dissipates, and because of friction and other things, well, from friction. But if you look at the concavity, well, one thing is we know if we look at the slope of the position curve, we can say something about the velocity. We hopefully know the slope of the position, the slope of, well, for one, the slope of the velocity curve versus time is the acceleration. That's one thing we know. But also the slope of the position curve is the velocity. So here we have a velocity of, say, 1 unit. Here we have a velocity of 0 because the tangent line is 0. Here we have a velocity of -1. Here we have a velocity of 0. But you can also look at the acceleration of the object by looking at the concavity of the position curve. So you don't have to actually look at the velocity curve. You can just look at the position versus time curve and make some comments about acceleration. So it all depends about, if this is the position, then the velocity is going to be the derivative. So I'm also going to plot the cosine of x. So you can see here's the cosine, which is the slope of the blue line is the slope of the red line. So here we have a slope of 1. So there's 1. Here we have a slope of 0. There's the 0 value. But again, we can just look at the concavity of the red curve to figure out what the acceleration is. So at this part of the curve, I think I'm going to move this down so I can reach it. Let me move my graph down or up, whichever way it goes here. There we go. Okay, so now I can reach it. So going from here to here, what kind of concavity do I have? Concave up or concave down? Down, okay. So a concave down curve has negative acceleration. Now when you get up here, I'm still concave down. I'm negative acceleration, but actually I'm speeding up in the opposite direction. So I have negative acceleration here, then I have 0 acceleration because there's a point of inflection here. And at this point I have positive acceleration because I'm concave up. And then I have positive acceleration here. I have 0 acceleration at this point. But if you remember in physics, we said that the sign of the acceleration, positive or negative, doesn't mean whether it's speeding up or slowing down. It also depends upon the direction that the thing's moving. So this is moving from, say, left to right. At this point, it's moving from right to left, right to left, right to left, left to right. You know, when it's moving, when the velocity is positive, it's moving one direction, and when the velocity is negative, it's moving the other direction. So it turns out if you have negative acceleration and positive velocity, it's slowing down. But if you have negative acceleration and negative velocity, then it's speeding up. It's just speeding up in the opposite direction. Then when you come down here and you have concave, the position curve is concave up, the acceleration is positive, but the velocity is negative. So again, this is slowing down. We're slowing down in this part of the curve. And then here we have concave up and positive velocity. In that case, we are speeding up. Okay, so I'm going to write what that all means. This is for physics people. Just to reiterate that negative acceleration does not always mean that it's slowing down. It depends on whether you have positive velocity or not. So let's make up a table. And the table probably is going to have the sign of the acceleration, the concavity of the position curve, the sign of the velocity, and what is it doing. Okay, so I need at least 3 columns, and I need 5 rows. Okay. Okay, so we'll say concavity of the x versus time curve. The sign of the velocity and some comment. Okay, so if the concavity of x is positive, or concave up, and the velocity is positive, then you're speeding up. You're getting faster if you had your speedometer. If you're concave cave down and your velocity is positive, then you're slowing down, speeding up, slowing down. If you're concave down and your velocity is negative, then you're speeding up. You're getting faster in terms of magnitude. And the final one is if you're concave cave up and your velocity is negative, then you're slowing down. So let's go back to the curve and see if we can figure out what's going on here. So using those rules, here I'm concave down. I'm concave down right there, and I have a positive velocity, so I'm slowing down. So this is the top. This is the spring coming up. As it gets to the top of the oscillation, it stops. So it's slowing down. Then when it starts to go the other way, falling down, what we have here is we have concave down, but we also have negative velocity, which I said was speeding up. So that's the downward motion of the weight as it goes. And then in the middle, you're going to, well, right here, you're going to be, well, let's just look at concavity. Then we come down here. So here we have concave up, but the velocity is negative. So we're slowing down. That's when you get the weight that's just about to the bottom of the cycle, and it slows down, and then it stops. And then we have concave, which one am I looking at here? We have concave up and positive velocity. So that's when the mass is going back up this way, and it's speeding up. So what it does when it oscillates, it speeds up to the midpoint, and you get the maximum velocity. Then as it comes up here, it slows down, stops here, then it speeds up, goes through the maximum velocity here, and then it slows down. So that's my explanation of, or trying to demonstrate that just because you have positive acceleration, it doesn't necessarily mean that you're speeding up. If we're driving a car and you think of positive acceleration, you think we're speeding up because we're moving in the direction that the velocity is in the direction that we're moving. So that's why intuitively this makes sense. Why we think that positive acceleration is always speeding up, but it all depends upon how you define your coordinate systems. Anyway, but the point for the calculus part is that we can look at this position versus time curve, and we can look at the concavity, and the concavity tells us what the acceleration of the object is. It's the second derivative. We'll probably talk more about that in physics, but that was just my little intro today. Okay. Oh, yeah, so let's, yeah, so let's just check out. We found out, we said that at x equals negative 0.79, we have a local maximum because it was concave down, and at 2.12 we have a local minimum. So here's the graph plotted. So here at negative something or other, we have a local maximum. It's concave down. Here we have the point of inflection, so it changes from concave down to concave up. And then we have a local minimum at x equals approximately 2. So that's the graph associated with the problem that we just did. And the points that we did, we found the point of inflection. We broke the interval up into two parts, from negative infinity to the possible point of inflection, and from possible point of inflection to positive infinity. We said everything in this interval is concave down, and everything in this interval is concave up based on the sign of the second derivative. And then we said, well, since this critical number is in this interval, it's concave down, which means it's a max, and the second critical number, which is here, is concave up, which means it's a minimum. Okay, so that's how that all works. So do the same thing for that. So what I want you to do is to find the point of inflection, make up the table to talk about the concavity. And actually, I'm going to change it slightly. I'm going to just change the sign of everything. So this is going to be negative. This is going to be positive. This will be positive. That'll be negative, just so it's pointing the other direction. So fill out the table relative to concavity. Also, find critical numbers and use second derivative test to determine which one is a maximum and which one is a minimum. So you'll take the first derivative, you can go ahead and set that equal to 0, solve for the values of x where it's 0, those are your critical numbers. Take the second derivative, which is the derivative of the first derivative, solve for there's going to be one value of x. That will be the point of inflection. You'll fill out this table with the second derivative information. So you'll have the interval from here from negative infinity to the point of inflection to the positive infinity. You'll pick a value of x in those intervals, see what the sign of the second derivative is, make some comment about concavity, and then relate the position of the critical numbers to which interval they're in as far as concavity, and then you can use that information to figure out which one's a local minimum and local maximum. And if you could do this, you can do really well in the next test, because I always put a polynomial on there. So, and you may have to use, you might be able to factor it for the critical numbers. Just looking at it, you might not have to use the quadratic equation. So anybody need any help or guidance? You can compare with your neighbors. Mm-hmm.
I wanted to ask if this was a correct setup to this, because I got -7 under that. Am I allowed to take out the 6's here to do this?
Well, you've got -4a. A is -1, so you're not you're gonna end up with a positive number.
Okay.
And I think you can factor that. If you divide everything by -1, you'll have x squared minus x minus 2. I think you can actually factor that. You don't have to use the quadratic equation.
Okay.
I mean, you can, but you don't need to. So here you go. So we take the derivative, we get negative 6x squared plus 6x plus 12. Divide everything by negative 6. You can factor that. So you get the critical numbers are x equals 2 and x equals negative 1. Then you take the second derivative, set that equal to 0. You find out the point of inflection, or possible point of inflection, is 1/2. So we create the two intervals between negative infinity and a half and positive infinity. Pick numbers in the two intervals, 0, 1. If you plug 0 into the second derivative, you get just 6, which is positive. And if you plug in 1, you'll get negative 12 plus 6, which is negative 6. It's just negative. And therefore, it's concave up like that. This one's concave down. So the question is, when you did the critical numbers, so let's see, Jacob. So at x equals negative 1, is that going to be a local minimum or local maximum? So which interval is negative 1 in? This interval or this interval? Right. And so what's it's concave up, which looks like that. So what's that, a minimum or maximum? Yeah. And therefore, the same reasoning. The second critical number is x equals 2, which is in this interval, which is concave down, so it's going to be a maximum. So that's how the second derivative test works. Okay. So I've got a handout here for you. Another one for you to work. What time is it here? 8:35. Okay. So this is not a polynomial. So I want you to just try to think about how you would do this. Let me give you 2 copies. You can give one to Summer. Savannah. They should have done their names with different letters. It's like Christian. Yeah, he has a brother named Kendall, right? Christian. You have a brother named Kendall, right? Yeah. So that's why I always confuse it, because Kendall is KK. So that must be the easier one that sticks in my mind. So I apologize for that. So don't ever your name. No. Let's see. Does anybody else have a name, their first name that has the same letter as their last name? It seems cute, but it's. So it says find the relative extrema for the function x plus 4 over x using the second derivative test. So it's exactly what we just did, except that it's not a polynomial. So you're going to, the way you handle this is you're going to rewrite the original function as x plus 4 times x to the minus 1 power. And go ahead and you can take the derivative of that. That'll be easy. You'll set it equal to 0. At that point, you'll have to combine the two terms with a common denominator. Did I forget you again? Yeah. Call me the wrong name. Forget to give me a paper. What's that? I was going to say I thought there was a song that reminded me of that. But there's there's the song that came to my mind was in Chicago. There's has anybody seen the musical Chicago? So you have Roxy, right? And you have her husband, the poor husband. And he sings a song. I think it's something like, is it Cellophane or something like that? Do you know that song? I think it's basically he's invisible. So Kendall's thinking, Christian's thinking that. Right? Just thinking that right now. I didn't mean to do that. It's like I cannot spell restaurant after almost 60 years. I cannot spell restaurant. It's just I spelled it wrong once. I can't, when I go, and it's very hard when you go on you're looking on your phone. I need to eat somewhere. Okay, let's go to Google Maps. Luckily, you just have to put RES in there and it works. If I had to spell restaurant, I'd probably weigh about 20 pounds less because I'd never find a restaurant. So yeah, anyway, take the first derivative, set it equals 0, but you'll have two terms here. Combine them into a single. The second derivative will only be one term because this one's going to disappear when you take the second derivative. But as far as find the two critical numbers, and actually, when you do take the second derivative, this is a case where the possible points of inflection are either where the second derivative is 0 or the second derivative does not exist. So it's the second case in this case. When you take the second derivative, it'll turn out that the value of x that is a possible point of inflection is where the second derivative is undefined. So I'm showing you here that when you take the first derivative, I just left it in the negative exponent form. So when you take the next derivative, you don't have to rewrite it again. But what you want to do is take the expression for the first derivative and rewrite that with a positive exponent. Set that equal to 0. Find a common denominator for the two terms, and then numerator, set the numerator equal to 0. Once you get the fraction that combines the two terms, it's going to be 0 when the numerator is 0. And it's going to be actually undefined when the denominator is equal to 0 and the numerator's not. So there are actually going to be three critical numbers from this expression. There's only one possible point of inflection here. But there could be three critical numbers. So this one you're going to do which one are we doing here? Is that for the second derivative? Mm-hmm. Yep. Yeah, you don't need all those spaces. I don't know why I put them in there. So yeah, you won't need all those spaces in the table. You would actually if you were looking at the first derivative, but if you're looking at the second derivative, you don't need to. So the reason I make this into a fraction, so what I did is I made 1 as x squared over x squared and then combine them, is that if I multiplied everything by x squared, I would lose this piece of information. I'd end up with just, if I took x squared times 0, I'd get 0. X squared times 1 would be x squared, so you'd end up with x squared minus 4, and I would only get these two values of x where there's critical numbers. But there's actually a third critical number, and that's where this function is undefined. When x equals 0, you're going to divide by 0, and so you miss, that's why you have to do that instead of simplifying it in another way. So I made the table up based on the second derivative, and so you go from negative infinity to 0, that's where f double prime is undefined, and from 0 to positive infinity, so those are the two intervals. If you pick negative 1x and you plug it into here, you'll get 8 divided by negative 1 cubed, which is negative 8, which is negative. And if you plug in positive 1, you'll get 8 over 1, which is positive 8. And so this is concave down because the second derivative is negative. This is concave up. Okay. So that's what else? So let's see if we answered all the questions. Set the first derivative equal to 0. Find the values of x where the derivative equals 0 or where the derivative does not exist. Okay. That's what that's what I did there. Those are your critical numbers. Take the second derivative. Find the possible points of inflection. So there was one possible point of inflection. It is a point of inflection because it goes from concave down to concave up. If a critical number is an interval of concave up, the x value is a relative minimum. So we can go back here. At negative 2, which is in this interval, we have a relative minimum, a maximum. And at x equals 2, which is in this interval, we have a relative minimum. At x equals 0, we don't have either one of them. Okay, so let's see if we can plot what this thing looks like. The last thing we want to do is find out what the value of the function is of the critical numbers. So the function, so f of negative 2 is going to be negative 2 plus 4 divided by negative 2, which is going to be negative 4. So you get negative 2 here. This is negative 2, so together they're negative 4. And f of 2 is going to be equal to 2 plus 4 divided by 2, which is 4. So we have the points, the actual coordinates of the critical numbers are negative 2 comma negative 4 and positive 2 positive 4. So those are the coordinates. So now we're going to add a piece of graph paper. it turns out we have a vertical asymptote at x equals 0, because if we go back to the original function here, wherever it is, oh, it's on my paper, when I have x equals 0, this goes to infinity. So we're going to have a vertical asymptote at x equals 0. So draw a vertical line. And we have a critical number at 2, 4. And we have another critical number at -2, -4. So if this is a vertical asymptote, this function has to come down to here. It can't come down from the other direction because you would have an x-intercept here, and there are no x-intercepts. If you set the original function equal to 0 and find the values of x where the function is 0, you'll find out that doesn't happen. And we know the function can't keep going down because we have a local minimum here. So it has to somehow go back up, and it looks something like that. Likewise, the function has to come from -infinity here. It'll go through this point, which will be a local maximum, and then it has to loop around and go back like that. And if you looked at the original function, you'd see there's a slope asymptote of x equals y. If you remember back to pre-calculus, you had different kinds of horizontal asymptotes, but you could also have a slant asymptote. And so this has a slant to it. So let's just plot it out and see what it looks like. So the original function was x plus 4 over x. X plus 4 divided by x. And we gotta zoom out. So there it is. And if I plot y versus x, you'll see, so I just plot x. You'll see that's there's the slant asymptote. So what calculus told us is that we had a local minimum at this point. The second derivative said it was a local minimum because we were concave up at that point. This one was a local maximum because we were concave down. We knew this had a vertical asymptote because the original function was undefined at x equals 0, and pre-calculus would have told us that there was a slant asymptote. So that's the two additional pieces of information we gathered from calculus. One is we have these local minimums and maximums, and also that they have to curve. They have to be curved this way, concave down and concave up. Okay. The last thing we're going to do in this section is look at a trig function. So we'll just start that. So this should look similar to one we did the other day. It's not exactly the same function, but it's similar to it. And we took the first derivative of the other function and set the first derivative equal to 0 to find the critical numbers. We're going to take the second derivative of this and set it equal to 0 and find the critical numbers. So it's going to be reasonably complicated. But the good news is I only put polynomials on the test. So as long as most people know how to take derivatives of polynomials, they can factor. Okay. So it's asking for the points of inflection, the intervals of concave up and concave down, and also to find the local minimums or maximums. So first derivative is going to be equal to 2 cosine x plus 2 cosine of 2x. So obviously that's, derivative of the sine is the cosine. Using the chain rule, the derivative of the sine of 2x is the cosine of 2x times the derivative of the argument. So that's the first derivative. The second derivative is going to be equal to -2 sine x minus 4 sine of 2x. So here, the derivative of the cosine is negative the sine. Here you have the derivative of the cosine is negative the sine, so that's where the negative comes from. So this changes from cosine to sine, and the derivative of 2x is 2, so you get a negative sign from the derivative of the cosine, and then you have 2 times 2 to give you 4. So those are the first and second derivatives. So to find the critical numbers, we set the first derivative equal to 0 and solve for the values of x where that goes to 0. And to find the points of inflection, we set the second derivative equal to 0 and find the values of x where that go to 0. And just like we did before, do you remember, what did we do last time? Do you remember? What do we have to do to this? You have to use one of those trig identities. I didn't bring my book, so that's probably a sign that we should stop there. So we'll continue on with this on Thursday. We'll find all the critical numbers. There's a lot of them. There's also a lot of points of inflection. And I already assigned the homework from this